All right. I am so back, baby. Um, so I haven't really thought about the problem at all. I'm still clueless as to why this is not working. I should probably exit out of some of these apps. Okay, so, oh, that is not what my screen looks like right now. Um, hmm. I feel like at some point I knew how to solve this. Aha! Okay, we got it. Great. Good stuff, good stuff. Okay. So we are here. 1705 is too high. So interestingly enough, uh, that's less than one banana per line. So that's kind of insane. That's kind of insane. The first thing I want to do is run this code here once. And then instead of doing this entire thing right here, I think it's going to be much faster to just go through all the keys of our dictionaries. So we got diff keys is an empty set. And then 4D, 4K, yeah, there we go. So then we can just say for diff in this. Much simpler. And perhaps even a lot faster. Who knows? I'm forgetting the word for. Man, this damn table is wobbly again. Wait, give me 1 second. Ah, it's not really getting better, is it? Let's see. Ugh. Okay, now it's better. So, let's see. Do we still get the same result? And is it maybe even a little bit faster? Perhaps. Perhaps. Yes. Yes to both. So, we got the right result for the example, which was 7. 23, I mean. Is a sequence always 4 numbers is a question. Four consecutive changes. All right, so 4 consecutive changes means we need to look at 5 numbers at all times, right? Huh. I think this might be 1000, blah, 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 blah. I mean, it has to be, right? The first 2000 numbers only have 1999. Oh, I get the same output. Uh, well, let's see. You're going to need as many bananas as possible, so you'll need to determine which sequence of 4 price changes will cause the monkey to get the most bananas overall. Each buyer is going to generate 2000 secret numbers after their initial secret number. Okay, so it's 2000 and not 2000 minus 1. And then the diffs, we append new modulo 10 minus n modulo 10. And then we append the new number modulo 10. I think that's right. 2000 changes. So we have 2000 diffs. I don't think we need this one. I think we just need this. And then we can do this. So is it len of diffs minus 4? I think it is. I don't see, I really don't see the problem in this. Approach. Huh. Um, I think we don't need these either. I kind of stand by it. Like we get 23 here, and I think we get 1705 for the real input. This is 22. Puzzle 22. And I got part 1 down. And we're currently looking at part 2. And this is the code I wrote. And if we run it on the example, we get the right number. But if we run it on our real input, we get 1705, which apparently is not the right output. You know, it's making me wonder if there's any chance we're not parsing the input right. No, I don't think so. Like I think if I just print if I just print the first number and the last number, I'm pretty sure this is just gonna work just fine. Yeah, that looks about right. That looks about right. So this is the iterate function. I mean, since we get the right value for easy, I think we're fine. There might be like an off by 1 error here somewhere. There might be an off by 1 error here somewhere. Like my logic is I'm going through all 2000 iterations and calculating the difference, and then I store the difference and the new value modulo 10 in a list. And then I'm going through the list with a stride of 4. And then I'm turning 4 values into a tuple, which then looks like this. So these are 4 values at a time of differences between numbers. And then I'm adding those to a dictionary. And then the value for the dictionary is the second value of the pair that we added to the diffs list. And the diffs contains a difference and then the new value modulo 10. So at the end of 4 differences, we get this many bananas or this much money or whatever. And then all I'm doing is I'm going through all the different differences we've seen and calculating the max of the current best value we've seen, and then the sum of dictionary.getDiff for every dictionary in our list. And then diffs, we just iterate over the numbers in T. Like this looks right to me. I guess I could say like the value is this, and then if value greater max v 0, we store value and diff so that we can print both. Just to take a look at what the sequence of diffs is that we land on. Just, because I'm curious. I just figured it out. 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 I'm overriding the diff with a later one, but we only ever take the first one that matches. Yes. Yes, 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 yes. So this should now be the right. I don't know why I suddenly just realized that that was the mistake, but I'm pretty sure we got it. Yeah. Great. That was pretty quick. So there's only 2 days left, 23 and 24. At day 22. And now let's take a look at 23. LAN party. Connection between 2 computers. Each line is 1 connection. LAN parties involve multiplayer games. Groups of connected computers. Start by looking for sets of 3 computers where each computer in the set is connected to the other 2 computers. There are 12 sets of interconnected computers. CG and YN. CG and YN. Because YN is also connected to CG? Yeah. I see. If the chief historian is here and he's at the LAN party, it would be best to know that right away. You're pretty sure his computer's name starts with T. So only consider sets of 3 computers where at least one computer's name starts with a T. Find all sets of 3 interconnected computers. How many contain at least one computer with a name that starts with a T? That's very easy to find out. So we parse it like this, and then connections is this, and then for left, right in T, connection left hand side is connections dot get left hand side plus right hand side, and then we flip the equation. And then I don't think I want to have it be a list. I think it should be a set. And then we do instead of this, I think you can join sets with a plus, no? Set of 1 plus set of 2. Oh, you cannot. Okay. Can you do this? Yeah. So it's just the OR operator. Great. Okay. And then for key in connections, and then for other in connections key, if how do we find 3? So we need to find all pairs of values. So that's like so how about we do for A in connections, for B in connections key, and then for C in connections key without B. I don't know if you can do minus set, whoops, of 1, 2, 3 minus set of 1. Okay, you can. So those are all possible. Nah, that's not great. I think I should do for I, B, and enumerate. Can you enumerate a set? Probably not. Set. Maybe you can. Print list of enumerate set. Yeah, okay. And then for C in range of I plus 1 and then len of connection C, C equals connections C. All right, all right. I think we should turn this into a list so it becomes, the order is consistent. For I, B, and others, for C in range I plus 1 len of others, if B in connections, let's just start by doing C equals others C index. And this is a list, of course. If C in connections B, then Um, threes. Threes append ABC. Or ABC and threes. If A starts with T or B or C, then the answer plus equals 1, print S, and S is equal to 0. I think that's it. Not it. Uh, hmm. I guess threes is a set. Still no. That's strange. Because we need to tuple sorted ABC. That's right. That should be right. I wonder what part 2 is going to be. The largest set of computers that are all connected to each other. Okay. That's also incredibly easy to find out. Is it though? Maybe not. Maybe not. We got 3,000 connections in our network. We could So we could just go through every single computer in our network. And then, no, it doesn't work. Maybe it does work. For every computer in our network, we try. Let's see, how many computers are there? Println of connections. 520. And what is the maximum len of v for v in connection dot values? 13. So if at most 13 computers need to be considered to be part of our network, that means we have 2 to the power of 13, which is about 4,000. It's like 8,000. So we have 8,000 different things to check for 500 different computers, which is trivial. So we should go and just build it. For computer, or let's call it start node in connections. And then we have n is the len of connection start node. And then for I in range of 2 to the power of n, list is the list of connections start node. S is a set. If I, for j in range n, if I and 1 j bit shifted, then s dot add l dot j. There we go. And then if all connected, s or set of start node connected equals empty list, or rather max connected equals 0 none. If len of s less than or equal to max connected 1, continue. If all connected, then max connected is this. Okay. Def all connected. L is list of s. Not sure if this works. I think it does. Yeah. There we go. Okay. And then we print what? What do we print at the end? Password is the name of every computer at the LAN party sorted alphabetically. Okay, so we print sorted max connected 1. Let's just turn it into a list to be safe. And then we join it with a comma. And then let's just sanity check if this set of values gives us the right output. But I feel pretty good about this one. This is not a difficult day. Yep, we got it. Add day 23. All right, let's take a look at the very, very last day and its logic puzzles. Oh, I don't really want to do this. How many? 300 lines. This kind of sucks. Wait, give me 1 second. Okay. back to business. So let's just read the whole thing because I'm definitely going to make mistakes if I just make assumptions. The device seems to try to produce a number through Boolean logic gates. Each gate has two inputs and one output. The gates all operate on values that are either true or false. AND gates output 1 if both, or XOR. You got it. Gates wait until both inputs are received before producing outputs. Wires carrying 0 and 1, blah, 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 blah. Because gates wait for inputs and wires need to be blah, 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 blah. After waiting for values on wires starting with Z, we have these values. Combining the bits from all wires starting with Z produces the binary number, which converts to 2024. Okay. So we do um, uh, so S is equal to read split new line, and then S1 and S2 are S split line, 0 and 1. And then we return the first one we split by this. Maybe int. By this. And then we return S2. Replace this with nothing. Replace this with nothing. And then we split by space. And we turn it into a string. So if we just print T0, 0 and T1, 0, we should get X0, 0, 1. Yes, there we go. Okay, so we ooh, okay. For key value in T0, whoop, in T0, val, there we go. And then for left hand side, right hand side, operator out in T1 if left hand side in val and right hand side in val while changed is true, changed is false, changed is true if and or XOR, is that right? I think that's right. And or XOR. Yes, 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 yes. All right, let's see if this works with the example input. Let's see if we run into runtime exceptions. We do not. However, and out not inval. That's right. All right, that's better. So now we go through all four sorted keys is sorted keys, and then s equals empty string for k and sorted keys. If k starts with z, then s plus equals val k. Nope, not right. Not right. Why is that? Oh, print k val k. Z0 is 0, C1 is 0, C2 is 0, C3 is 1. That looks right to me. Combining the bits from all wires starting with Z produces the binary number this. Well, I disagree, because isn't it supposed to be... Oh, it's reversed. Oh. So now it's 2024. Okay. Great. What's part two? It is treating the bits on wire starting with X as one binary number, treating the bits on wire starting with Y as a second binary number, and then attempting to add those two numbers together. The output of this operation is produced as a binary number on the wire starting with Z. The initial values for the wires in your puzzle input represent just one instance of a pair of numbers that sum to the wrong value. Ultimately, any two binary numbers provided as input should be handled correctly. That is, for any combination of bits on wires starting with X and Y, the sum of the two numbers those bits represent should be produced as a binary number on the wire starting with Z. For example, if you have an additional system with 4 X wires, 4 Y wires, and 5 Z wires, you should be able to supply any 4-bit number on the X wires, Y, and on the Z wires. One of the many ways you could provide numbers to such a system would be to pass 1, 1 on X, no, 11 on X, 1, 0, 1, 1, and 13 on Y. If the system works correctly, then it should return 24. Unfortunately, your actual system needs to add numbers with many more bits and therefore has many more wires. Based on the forensic analysis of scuff marks, you can tell that there are exactly 4 pairs of gates whose output wires have been swapped. I see. Okay, well, do we just put in random numbers and we hope So we can identify the 4 wires that need flipping. I mean, how many different wires are there? We got 222. So 4 gives us 222 times 221 times 220 times 219, which is a little too many combinations. Oh my God. How many people are struggling with this day? 10,000 people have solved it by now. That's a lot of people. Just give me 1 sec. Okay. Let's see. So we kind of actually have to figure out. I guess one thing we could do is walk along the wires, like go along the bits, right? So we would figure out if for any given number, if we add them together, we get the right um, bit in the nth position. And we just figure out which bits are wrong. So we could just try flipping random wires to figure out if the amount of wrong bits goes down. But that doesn't sound very efficient. What does flipping a wire even mean? How were the wires messed with? They got their output swapped. Okay. Swap output wires AAA with EEE. The first pair of gates with swapped outputs is this one and this one. So this one now, okay, I see. So we swap. Yeah, that makes sense. So we could. I don't know if it's going to be that easy that we just swap 2 random wires and we see um, if the amount of bit errors goes down. That sounds too easy. I don't think that's going to be doable. Um, or maybe it's doable. I mean, we could give it a try. So let's just try swapping one wire and running it on the example and seeing if this works. So we would do that by um, let's see. So let's call it count bit errors for any t. Um, so we would do this, and then we would say we would say so this is going to be z. And then we do the same thing for x and y. Is that right? Is it x, y, z? Yeah, x, y, z. And x. X, y, z. X, y, z. And then we got true z is this. Is bin a method? Does that work? Can you turn 7 into 111? Yes. Okay, okay. And then we cut out the first two characters. And then we do if len of true less than len z, then true, yes, yes, yes. And then we do the same thing the other way around. Great. And now bit errors 0 for I in range this. There we go. And then we return bit errors. Great. So let's see. Print count bit errors of t. 6. 6. Okay. Let's try. For I in range len of t1, for j in range I plus 1 len t1, and then we do t underscore 1. Is that right? Was this swapping I and j? T1I, T1j. No, because it's swapping the entire line, but we only want to swap 0, 1, 2, 3, the third element. There we go. All right, and then we reverse it later. And then we print count bit errors. I don't think I need to deep copy right now. Let's just try this. Why is this happening? Because count bit errors has prints in here that are not supposed to be there. Okay. I think there's even more printing still happening. Yeah. Okay. So now we're trying to swap I and j. So min is count bit errors, none. And then if new error is this, if new error less than min, then min is ij. And then we print min, just both. Let's see. So after swapping one wire, there's only one error left. Okay. So then ij is min 1. We swap them. And then we do the same thing again. Print min. Should be 0. Yeah. So we got first flip is this. Okay, so let's put it in a loop. Swaps equals empty array. For underscore in range 2. Swaps append ij. Print swaps. I think that's right. Except it's not right because we want to print the strings. So we swap B, F, W, and T, and W. Is that right? What example am I looking at right now? NTG XOR FGS. So they're not giving us the right answer for this example. So, let's just see what we get for the real thing. I mean, how long could this take? This is not going to take too long. What did I say? 222 wires? Um, I see. So that did not work. That did not work. Ugh. So we're finding two wires to swap for the first and the second and maybe the third. No, the third one breaks. So the first two times we found two wires to flip, but then we didn't. Okay, let's try again. Let's swap different wires. Ah, we still have one bit error. That kind of sucks. That kind of sucks. We're close. We're very close. Wait a second. So we're just swapping the same two wires back at the end. So these two are obviously just wrong. So we can't be greedy. We can't just swap the wires that give us the smallest bit error, which makes sense. That would have been a little easy. So I'm not quite sure how to solve this one. I'm not quite sure how to solve this one. Um, how many registers are there that are not X, Y, and Z? A lot. How many? So we got 44 Ys and 44 X's. Let's see what ChatGPT has to say about this. Let's say we want to build a full bitwise adder for two values that have 44 bits. How many statements of bit and operation bit m, no, let's call it bit c equals bit a, b, what we need for this, assuming operation can be and or and XOR. Just 1 second. Okay. A full bit adder operates at the bit level and computes the sum temp sum is bit A XOR bit B. Compute the carryout. Each bit requires 5 statements. That's a lot. 220 statements. Yeah, that's about what we got. But we got 2 extra, I guess, which is a little confusing. Which is a little confusing. Uh, temp sum is equal to bit A XOR bit B. Is that the only XOR in the whole thing? No. Well, the easiest way to define dude, what the hell is carry one? Oh, I see. Hmm. Full bit adder. Okay, I think I have an idea. Like, I think the idea is that we go through. So the easiest statement to identify is XORing 2 bits. right? So that's always going to be an x on one hand and a y on the other side. So we we would go about it like this. So we have this. If LHS starts with X and RHS starts with Y, then we just print the whole thing. Let's see what we get to. Yeah, that looks about right. Other and that's a little weird. Is it always XY? No, it could also be YX. All right. So we just execute it twice. And op equals XOR. And left-hand side ends with right-hand side. There we go. Then we want to call whatever comes out of this one. What do we call it? We call it the temp sum and then the number. The to name is a format string of temp sum. Yeah, sure, this. From name is out. And then we just do for line in T1, for I in range of len of line. If line from name, then line is to name. And then we just do the same thing. And we say LHS, RHS is RHS, LHS. So I guess we could just do it twice. For underscore in range 2. And then we just swap it like this. There we go. Okay. So now we print T1. Let's see what we get to here. Print out is equal to this. Let's see. And we do the same thing with and. Except for and, we don't call it temp sum. we call it carry 1. There we go. We're starting to get there. We're starting to get there. We're still ordering carry and something because carry 2 is carry in and temp sum. So temp sum, temp sum, temp sum, temp sum. Temp sum gets XORed with carry in. Temp sum gets XORed with carry in. Let's see. So how do we do this? If left-hand side starts with temp sum and operator is and, then we replace right-hand side temp sum and with carry in and then the number, maybe. If left-hand side starts with temp sum and operator and carry in, toName is carry in. Left-hand side -2 colon. From name is right-hand side. Let's see. Carry in. Okay. And then carry in and temp sum is carry 2. So we can now do carry 2 for the output, I think. Yeah, that looks about right. That looks about right. Okay. So now, um, I think the only thing that's missing is we're not doing, yeah. Oh, okay. No, 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 we are doing everything. So why is there still a value that's not getting replaced? BHD. What the hell is BHD? tmp.txt. And then we code tmp.txt. What the hell is BHD? Carry in 1 XOR temp sum. I think there are supposed to be 2 statements in here that, it's BHD and this one. Those 2 are weird. No, there's more. There's also this one. Okay. So what's going on here? What's going on here? These must be the errors then, right? Yeah, this is not right. No, this is right. This is right. Man, I feel like I'm going crazy looking at this stuff. I'm going crazy. Can we sort these? That looks more like. There we go. I mean, there we have our four mistakes. These and BHD. Do we just print those? I don't know. No, I don't think that's right. I think we have to take a look at um, the input values. Like there has to be something swapped with the input values. So we got 8 different candidates. It could be those 8 different candidates. So we could try to just find any combination of 4 different values in those 8 different inputs, and that's probably one of them is right, if I had to guess. So how do we go about doing that? Well, we could um, we could do matches equals set, and then we just matches dot add this thing. Here it's also out. Here it's right hand side. And here it's out. And then for all of these, if out not in matches, print out. So we get 4. No, that's not right. Okay. Okay. Ah, I see. I see. So it's not quite that easy. Um, so how about we do temp sum Let's try this one. Dim sum is a set. Yeah, that looks more like it. So temp sum add this little guy. And then this is just others. Matches dot add this in temp sum. And then RHS and out. Other matches. RHS and out. There we go. No. Yes, no. If out in other matches or temp sum. Print out. Not in. So this should now hopefully be exactly 4 values. Nope. Wrong again, buddy. God damn it. Wrong again. Why? How? I feel like that was exactly what we did here. If out starts with Z, continue, starts with X, starts with Y. Okay, so now we got 4. I don't think that these 4 are the right answer. For example, the system below is supposed to find the bitwise AND of the 6-bit number. What? Could be anywhere. Wait, are we doing a bitwise adder? I think we are, right? Add 2 binary numbers. Yeah. Yeah. Add those 2 numbers together. Okay, well, I want to see if swapping. Okay. I think it's probably the easiest to just run this and see if we get the right answer. In this example, 2 pairs of gates that are swapped, sorting the output wires names and joining them. Let's see. To print is equal this. To print and out, and then print comma dot join sorted to print. Don't think it's right. Had a feeling. But I think that all of the inputs so we have candidates equals a set. And then we say candidates dot add out. And then also LHS and RHS. And then we try to get any four different values. So we say so we got 4 with 2 inputs, so that's 12 values. So 12 times 11 times 10 times 9 is 11,000. That's not too bad. We can run 11,000 different ones. So okay, well, first of all, candidates equals list of candidates for I in range len of candidates, or j in range, yes. For k in range j plus 1, and for L in range k plus 1. And then we swap. How do we swap again? I think we swap with I don't think we want to add candidates equals C for C in candidates. We do T1 index of C, except it's not T1, it's line -1 for line in this. That's more like it. All right, so then we swap T1 I, no, candidates I. And then I think it's 3. Is that right? 0, 1, 2, 3. Yay. IJ is equal to JI. And then we do the same for K and L. I becomes K, J becomes L. And then we swap back after. If bit error is T is 0, print 0. Return. That doesn't seem right. Else print no. Ay, ay, ay. So that's not the right answer. This seems way short. I thought we had 12 candidates. Do we have fewer? Print len candidates. $11. Well, still, I mean, that's 11 times 10 times 9 times 8, which should be 7,920. But we're not getting 7,000 outputs here. We're getting way fewer. For I in range len candidates, for j and I plus 1 len candidates, for k and j, and then for l and k plus 1. I see. This part is wrong. If I, j, or I, k, or I, l, or j, k, or, is that right? I has 3 different things that it can be equal to. That's right. KLM, no, JKL. J has 2, which is KL, and K has 1, which is L. Okay. Still nothing. I'm fucked. I'm absolutely fucked. I is J, J is I. K is L, L is K. Man, what the hell? What's the minimum we get to? Probably 2, 5. Oh, that's worse. That's worse than the approach we had before. We did better with my last idea. Maybe I did get the right answer with my last idea, where we ended at 1 bit error. Maybe maybe that was the right idea. Because this clearly wasn't. Okay, I wonder if it gets better or worse if we just remove these. 8. And then if we do this, 6. So we're closer to the right answer if we just take a look at the inputs and not the actual wrong ones. I don't know, man. I don't know. I think I'm gonna take another break. I think I am. That might be a good idea. Ugh. We're this close. I can feel it. I mean, we're literally one bit away. I think once I get back from my break, I'll be trying my previous approach again, which was to just try randomly flipping two cables and then seeing um, what the minimum amount of wrong bits is. And since we got further to the right answer by flipping the minimum equation from less than to less than or equal, my theory is that if we just take a look at all of the candidates that produce the minimum amount of bit errors after flipping, um, we should definitely be able to get to the right answer. Because if we're just one bit off, that's like really good. So I think it's worth giving it a try. All right, I'm going to take a break and I'll probably be back in a bit. Bye-bye.